Welcome back, students. In this video, I want to go through Sn1 and Sn2 mechanisms in a way that is going to help us figure out which mechanism is going to happen when we're given an example. Let's start by showing an example. Here's an example of a potential substitution reaction. What we want to do is be able to look at all the information that we're given and decide whether or not an Sn1 or Sn2 mechanism is going to happen, and then figure out what the product is going to be. Right now, I bet that we wouldn't feel very confident figuring out if this is going to be an Sn1 or Sn2. What we need to do is look at all of the information that's available and then use those as puzzle pieces to figure out whether or not an Sn1 or an Sn2 mechanism is going to occur. And yes, it does matter because they have different products and different stereochemistries. The first thing that we're going to do is look at the substrate, then we'll look at the nucleophile, then the leaving group, and finally the solvent. I want to start first by looking at the substrate. Remember, the substrate is just the fancy word for the electrophile. An Sn1 mechanism is going to require a hindered substrate, so something that's more substituted. When we look at a hindered substrate, what we're talking about is tertiary or secondary, something that's going to form a stable carbocation, right? So that's our goal here. We need to form a stable carbocation. Whereas Sn2 reactions are going to require an unhindered substrate, something like methyl or primary. Because the nucleophile is going to attack the electrophile from the back side, we need as little electron density around that alpha carbon that the nucleophile is attacking as possible. So here, because of backside attack, we need an unhindered substrate. Methyl and primary substrates are going to lend themselves to Sn2 because these are unhindered. Tertiary is going to lend itself to Sn1 because you're definitely going to get a stable carbocation, but you can't have Sn2 for tertiary. Secondary is where it gets tricky because you could have both. You could have Sn2 happen, or you could have an Sn1 happen. And that's where you need more information. Allylic and benzylic are also tricky because they could also have both. So here you could have Sn2 or you could have Sn1. One thing that I do want to point out is when we're starting to look at allylic and benzylic, if we consider something like this for allylic, when that iodine leaves, that iodine is going to create a primary allylic carbocation if it leaves on its own, right? So if it does this, and you get a primary allylic carbocation, the fact that it's allylic means that Sn1 is possible. Right? So I don't want you to look at it and go, oh, it's primary, so you can't have Sn1. No, because it's in resonance, you can have Sn1. Now let's look at nucleophiles. In general, your Sn1 reactions correlate with weaker nucleophiles, and that's because the leaving group has already left. You have now a carbocation intermediate, which is an incredible electrophile. So you don't need a strong nucleophile to react with that incredible electrophile. As soon as that carbocation forms, boom, something's reacting with it. Whereas for Sn2, because you are forcing out the leaving group, you're going to require a stronger nucleophile there. Now, depending upon the textbook that you're using, sometimes certain textbooks or certain professors will classify as strong nucleophiles, moderate nucleophiles, and weak nucleophiles. I mean, I'm not that person. I don't have time to memorize also the ones that are moderate. Who cares? We're just going to call them strong and weak. Let's look at the list of strong nucleophiles and try to make sense of them so that we feel like we have less to memorize. When we're considering our strong nucleophiles, see how we have the halogen family right here with the exception of fluorine because fluorine is weird. So here we have the halogens without fluorine. Then anything that has a sulfur in it is going to be a nucleophile, a strong nucleophile. So these are sulfur compounds. Negative oxygens and then this NC minus, I'm just going to redraw this one down here. So you see N triple bond C. So we have our set of strong nucleophiles, and instead of memorizing them, if we can just remember halogens minus fluorine, sulfur compounds, whether they're neutral or negative, and negative oxygens are going to tend to be our strong nucleophiles, and then we'll throw in Cn minus. The weak nucleophiles are going to be fluorine, so fluorine is a weak nucleophile, that fluoride ion, and then neutral oxygens are going to be weak nucleophiles as well. The next thing that we're going to consider is leaving groups. You need a good leaving group for both Sn1 and Sn2 reactions. But if you had to make a choice, Sn1 is more important to have a good leaving group, like a really good leaving group, because the leaving group is leaving on its own, right? In Sn2 reactions, the nucleophile is coming in and it's forcing out the leaving group. So if you only had the option of choosing an excellent leaving group for one or the other, I would choose it for Sn1. But in the grand scheme of things, you need a good leaving group for both of them. And if you have a crap leaving group, then the reaction's not going to happen. Here are some examples of some good leaving groups. So our strong leaving groups are going to be, again, halogens minus fluoride. Fluoride stinks. Water is a great leaving group, and then this one is new, this OTS. I'm going to redraw this one. The way it's abbreviated is OTS, where that line that I drew on the left is the bond where it's connected to the alpha carbon. OTS is called the tosylate ion. It's part of a sulfonate series, and the reason that we don't draw it out is because it's obnoxious. So this is what OTS looks like, where over here I'm going to put an R, and that's the carbon, the alkyl portion that this is bound to. So you can see why we abbreviate it as OTS. Our poor leaving groups are going to be things like hydroxide or any alkoxide, and alkoxide is the fancy chemistry word for something that looks like hydroxide, except the H is replaced with an alkyl group, right? So alkoxide, it's like alkyl oxygen that's negative. That's what it's called. And then an NH2 group. The final thing to consider is solvents. Solvents make a bigger difference than you realize. There are two classifications of solvents. There are polar protic solvents. So these are polar solvents that have the ability to hydrogen bond because they have an electronegative atom attached to a hydrogen, right? So they have an OH, NH, or FH bond. Whereas polar aprotic solvent, that A means not, right? So polar aprotic solvents mean these do not have the ability to hydrogen bond, because although they might have an electronegative atom, that electronegative atom is not connected to a hydrogen. Here are some examples of some protic solvents. Water and alcohols are great ones, and then there's also some nitrogen containing ones. And then we have a huge list of aprotic solvents. There's a lot more examples of aprotic solvents here than our protic solvents, and some of them are a little tricky in the sense that the structure for them isn't drawn. Like we didn't draw the structure for acetone. This one is called acetonitrile. And so sometimes you'll see people write the name, sometimes you'll see people write the structure. DMS is dimethyl sulfide, THF is tetrahydrofuran, CCl4 is carbon tetrachloride, CH2Cl2 is called dichloromethane, some people call it DCM, and DMS I already have over here, that's a duplicate, and DMSO is dimethyl sulfoxide. So these ones, they have these horrible abbreviations. You can't even look at the structure and say, oh, that is clearly an aprotic solvent, because there's no electronegative atom bound to a hydrogen. So unfortunately, you have to memorize these, or the other thing that you could do if it helps you is to look up the structure of things like DMS, THF, and so on, so that you can see in your brain and remember that these are aprotic solvents. Let's talk about why protic versus aprotic solvents are going to be helpful for these different reactions. So when we look at Sn1 reactions, our polar protic solvents are the one that we want. When we consider these Sn1 reactions, remember we're creating a carbocation during this reaction, right? That's the first step. The leaving group leaves, you make a carbocation. Carbocations are notoriously unstable. Anything that we can do to help stabilize the carbocation is going to be good. So for Sn1 reactions, we want to help stabilize the carbocation. We're going to do this by utilizing a polar protic solvent. The polar protic solvent will then hydrogen bond to the carbocation. So I have this positive charge drawn here. That's supposed to be my carbocation, and my polar protic solvent of water is hydrogen bonding to my carbocation to help stabilize it. So in this case, hydrogen bonding to our carbocation is good, it makes us happy, and it will stabilize the carbocation that has formed. Stabilizing the carbocation is good, it means that that carbocation is probably more likely to form. Then when we consider Sn2 reactions, where we have polar aprotic solvents, we are not forming a carbocation. We instead are having a negative nucleophile do the attacking. And what will happen for aprotic solvents is the aprotic solvents will surround any positively charged entities in the structure because you have this partial negative here. And you're probably looking at that going, well, I mean, what about sulfur? You know, sulfur, if oxygen has a partial negative, doesn't sulfur have a partial positive? Yeah, but that sulfur is in the internal of the molecule, so it's not going to be able to stabilize anything very well. And also it has a pair of electrons, so it's definitely not going to be very much involved. So if we compare what's happening, I'm going to bring your attention over to this side now and this side. In your Sn2 reactions, your aprotic solvent is surrounding any positive ions, which is fine because those positive ions, if they're in there, are just spectator ions. And notice how nothing is surrounding the negative ion. That's good because for Sn2 reactions, we want a strong nucleophile. A strong nucleophile is one that is, in a way, naked. And I say naked because if we compare what happens with a polar protic solvent to your negative nucleophile, what's happening is your negative nucleophile is hydrogen bonding with the polar protic solvent, like I just put in the top yellow box. That's creating something called a solvent cage. So the negative nucleophile, and even if it's not negative, even if it's just a plain regular neutral nucleophile, the polar protic solvent is still surrounding it. It's making a shell around it. And in order for that nucleophile to attack the electrophile, it would have to shed its cage first. And in Sn2 reactions, the nucleophile strength is really important. It's part of the rate equation. So having a weak nucleophile will really slow down that reaction. Therefore, we need a strong nucleophile for our Sn2 reactions. And one way to have a strong nucleophile is to use a polar aprotic solvent that's not going to surround your nucleophile in a solvent cage. I want to explain this in a real life example that might make more sense. Imagine that you are a track runner. When you are running track, if you are running just in your fancy track clothes that have no drag and they're very tight, or whatever track runners run in, I'm not a sports person, then you're going to run fast. That would be like if you were a nucleophile in an aprotic solvent. You're going to be fast. But if you are a track runner who has one of those parachutes attached to their back, that's like your solvent cage. In order to run fast, you have to shed that parachute or shed that solvent cage and end up then bolting and making it happen and reacting. That's difficult to do. So when we look at Sn2 reactions, when we need a strong nucleophile, we choose the aprotic solvent because the aprotic solvent doesn't interact with the nucleophile. Whereas if we chose a protic solvent, the solvent would interact with the nucleophile and slow it down. So let's recap really quick. Polar protic solvents are good for Sn1 because we want the protic solvent to interact with the carbocation to stabilize it. Polar aprotic solvents are good for Sn2 because we don't want the solvent to interact with the nucleophile and slow it down. There's one other interesting thing that happens. When we look at halogens, the halogen reactivity goes like this. In polar protic solvents, your iodide is going to be your most reactive. That's because it's the best nucleophile. It's big and it's squishy. You remember the big and squishy video? When we looked at big and squishy, we said that that had to do with polarizability. That the iodide ion was large and it had the ability to have some external force manipulate its size and shape. So iodide is your best nucleophile of this set. When we're in an aprotic solvent, it actually switches. And your fluoride ion becomes the best of the nucleophiles, and then the chloride, and then the bromide, and then the iodide. Why would that be? Well, what's happening in your aprotic solvents is your aprotic solvents don't have that ability to surround the nucleophile. And then your iodide, which is the least stable of this set of ions, ends up being the most nucleophilic here, or the most reactive, because it is the least stable. And it's going, oh my gosh, nothing is surrounding me. There's no solvent surrounding me, protecting me, and helping me. I need to freaking react. Right? So that's what's happening when your iodide ion is no longer surrounded by solvent. So one more time, in polar protic solvents, what is happening is we're seeing the halogen reactivity mimic nucleophilicity, right? So which one's the stronger nucleophile? When we take away that polar protic solvent and we add an aprotic solvent that is not interacting with your halogens, because those are negative and your aprotic solvents aren't doing that, then your fluoride feels naked and nothing is stabilizing it, so it has to react in order to become stable. Let's wrap up. In this video, we looked at 4 factors. We considered the substrate, the nucleophile, the leaving group, and the solvent, and how they all interact with Sn1 and Sn2 reactions. Now I want to go on to another video where we're going to look at some practice where we actually employ these ideas. Thanks so much for your attention. This is Katoni signing out.